So let's just go a little bit more general. What we did before was we looked at the specific example of a binary feed-forward neural network with one hidden layer for classification. You can kind of use many more layers in between, and so this figure kind of illustrates a multi-layer feed-forward neural network. So what we could have done here is instead of just one layer, we could have added a second one and a third one and a fourth one, okay? And you get multiple layers, okay? Or on your vector diagram, you would just have more blue vectors here. In the computational graph, so now I've kind of flipped it horizontally. In the computational graph, this would be one layer, and then you would have a second layer, and then a third layer, and so on, up to right at the end. Here in this graph, I just used the squared loss at the end because I want to show you that you can, by just changing the loss function here, you can actually do regression instead of classification. And all that I had to do was I defined a different operation here right at the end of the graph. And as long as I can calculate the partial derivatives of the output with respect to the input of any computational node, I can apply exactly the same algorithm that we looked at before. So here in this case, we've got a multi-layer feed-forward neural network with L-1 hidden layers, okay, where each layer looks like this. Z1 basically takes WL and multiplies it with that, adds the bias, and then you apply the nonlinearity, and then you get the output of the Lth layer, like little Lth layer. Okay, and you can apply this again and again and again. To summarize the error signals for this kind of middle layer somewhere, all of the layers will have the same error signals, and they will all look like this. So the error signal of ZL will just be the error signal of A, this one, with the element-wise multiplication of the derivative of your nonlinearity, and then the ZL there. The error signal for BL and ZL, that's really easy because that just goes straight through. The error signal for WL, you can write that out. So, sorry, there's a little bracket missing there. You can write that out, and we've looked at this example before, but this is just the error signal of ZL times AL minus 1 transpose, okay? And then the error signal for AL minus 1 is just the error signal of ZL, this one multiplied by WL transpose. And the cool thing here is that you can actually combine all of these equations into kind of one equation looking like this. So if I just look at the error signal for ZL, the error signal for ZL is the element-wise multiplication of Z, and I've got this thing, okay? And then where do I get this error signal from? Well, that comes from the layer that's on top of it, okay? And that layer's error signal looks exactly like this equation, so we can stick that in there, okay? All the L's goes to L plus 1 because we're looking at the layer that follows this one, and we get this expression here. Now, what's useful about this is that this really highlights the kind of the recursive nature. If you have a feed-forward neural network where every layer looks the same, where every layer has the same structure, then you end up with the equation like this that describes the error signals for an arbitrary layer. And I should also say that this is really, if you look at the kind of classic way, the early 90s way of explaining neural networks, they would actually probably go directly to this shape or kind of try and derive this directly instead of using this graph formalism that I've used. But I will explain in the next video why using the computational graph view of neural networks are so useful.